On October 2nd, something happened so fast over Mars that in a time-lapse video, the stars seemed to move backwards. Amateur Stefan Burns put together a 9-minute clip with raw images from the Perseverance rover, and there it was, a trail about 60 miles away. The next day, other observers noticed something even stranger. It looked like several objects at once, plus a brief green flash that's hard to explain naturally. By October 3rd, Mars Express, TGO, and HiRISE were supposed to give us the best close-up images of 3I atlases, but there was silence, no data released. Meanwhile, Avilov from Harvard shared a calculation showing a 0.6% match with the direction of the famous WOW signal from 1,977 inches the spectra. The CO2 surpasses water in an 8-to-1 ratio. Nickel is detected coming from the coma without iron, and the tail points in an unusual direction. Now the object is behind the sun, heading toward perihelion. What will emerge from the solar glare in November? That's what this video is about. We're not chasing sensationalism, but reviewing the facts step by step. Every oddity might have an explanation until maybe there are too many. We'll gather all the footage from Mars, the spectra, the orbit evolution, and the observation schedule. And you'll decide the conclusion, a single comet or something more complex. So let's go back to the starting point. That night when a simple amateur time-lapse raised the first question. Chapter 1. Wait, are there several? Let's go back to the moment it all began and set the facts straight so we don't lose track. The 2nd of October, 2024. Stefan Burns, an amateur who processes space data and one of thousands who daily review NASA's open archives, downloads raw images from the Perseverance rover's navigation cameras on Mars. For him, it's routine to look for atmospheric phenomena, occasional meteors, or, if lucky, a dust devil on the horizon. He compiles a 9-minute time-lapse of exposures and at first sees what's expected: stars sliding due to Mars's rotation, since the rover has no equatorial mount and stays still on the ground. Then he applies star field stabilization, a classic trick where software identifies reference stars and aligns the frames so the background stays fixed. Everything that isn't stellar atmosphere, faint trails, artifacts, stands out, and then the key detail appears. In front of him, there's a trail, very fast, really fast, moving at about 37 miles per second relative to Mars, according to initial estimates. And it doesn't behave like a typical meteor. The trajectory is too straight and steady to be a random atmospheric event, and it doesn't match any artifact in local orbit. No satellite around the red planet moves at that angle and speed, so the explanation, Mars hardware, doesn't fit. The reasonable hypothesis points to 3I atlases, the interstellar object expected in the field of view around those dates. This would be the first recording of an interstellar comet from the surface of another world. So far, everything looks clean. Correct methods, consistent data, and an impressive result. But a few hours later, something emerges that changes the tone of the conversation. Burns posts the video, and the community reacts instantly. In the next 12 hours, other processors upload their versions of the same raw files. Some try different stacking methods, others enhance weak signals, adjust gamma curves, and aggressively boost local contrast. Suddenly, in several processed versions, not one, but several trails appear, 2 or even 3 additional ones, weaker and less sharp, sometimes almost parallel to the main one, but not fully synchronized, and apparently at different distances. The obvious question, are these optical ghosts created by the algorithms? There are many plausible sources. Compression artifacts in transmitted packets, hot pixels on the sensor, cosmic ray hits during exposure, even dust on the optics lit at an awkward angle could draw misleading lines. Still, we can't rule out physical alternatives because comet history knows about breakups into swarms of fragments. Remember Comet 73P divided by Schwarzmann-Walkman in the mid-90 seconds, which broke into dozens of pieces, and we saw its caravan for years. If 3I atlases suffered tidal stresses near a massive body, or internal stress entering the solar system, fragmentation is plausible. There's also the scenario of smaller objects, moving in tandem, though the configuration looks suspiciously orderly, bringing us back to the processing dilemma. The honest stance is to record the facts, carefully separate assumptions, and not jump to conclusions until independent confirmations arrive. Right then, another strange detail complicates the picture. In a single frame, and only that one, there's a very brief green flash next to or inside the main trail, lasting less than a second and at the noise threshold. Several independent analysts pointed out that emission, and with maximum enhancement of the red, green, and blue channels, the trail remains visible. Green in comets is well known, the fluorescence of dicarbonyl radicals, or sometimes atomic oxygen produces emissions around 515 to 520 nanometers. Last year, Comet C divided by 2022 E3ZTF had a bright green coma, and there's plenty of literature on the subject. The problem is that spectroscopy of 3I atlases at those dates, for example from Magdalena Ridge and Lowell observatories, showed no significant dicarbonyl lines. Carbon dioxide, cyanogen, and sodium lines appeared, but CO2 was absent or too weak to confidently detect. What could have emitted green if not dicarbonyl? Atomic oxygen is possible in theory, but to see a green OI line from about 1.5 astronomical units away, a specific excitation mechanism is needed, which other instruments should have picked up. The less romantic alternative is a sensor fault, a pixel anomaly, internal reflection in the navigation camera's optical chain, or a statistical fluctuation in the Bayer matrix at the sensitivity threshold. The right approach is to admit uncertainty and not embellish results unless there's independent duplication. Normally, the next step is taken by professional instruments, orbiting cameras, high-resolution spectrometers, and detailed series from Mars Express, the Trace Gas Orbiter, and HiRISE on the Mars Reconnaissance Orbiter. These platforms were precisely supposed to observe 3I atlases on October 3rd, when the object passed about 1.7 million miles from Mars, a tiny distance on a planetary scale. And here we arrive at what some already call the Martian blackout. But first, it's worth sorting out the state of the evidence. The multiple objects hypothesis is possible, but lacks independent confirmation and critically depends on processing algorithms. The green flash is suggestive but hasn't been reproduced in other series, and lacks consistent spectroscopic support. The speed and trajectory of the main trail fit well with 3I atlases ephemerides, giving us a solid point. In sum, we have anomalies that are more questions than evidence for now, and each question leads to another piece of the puzzle. In the next chapter, we'll need to examine why orbital data hasn't appeared publicly yet and what that delay might imply for the whole story. Chapter 2. The Martian Blackout. This is how it was supposed to go down, and it's important to set it precisely before drawing conclusions. The 3rd of October 2024. 3I atlases passed its closest approach to Mars, roughly 1.7 million miles away. In spatial terms, that's almost a near miss. Orbiting were some of the most powerful cameras humanity has sent to another planet, so expectations were high. HiRISE aboard the Mars Reconnaissance Orbiter reaches resolutions around 1 foot per pixel. On the surface and, looking into the background, distinguishes structures several kilometers across. If 3I atlas's nucleus measures between 3 and 6 miles, that optics could even suggest its shape and signs of outgassing jets. Also available were CASIS on the Trace Gas Orbiter and HRSC on Mars Express, expanding the possible data range. CASIS is a stereoscopic color system with 4 channels plus 1 panchromatic, designed for 3D mapping, but it can also track bright targets in deep sky with suitable filters. It can highlight specific molecular emissions, providing clues about the coma. HRSC on Mars Express, veteran but reliable with 9 sensors and a wide field of view, is ideal for capturing extended structures like comet tails. The 3 platforms were supposed to observe 3I, Atlas, and schedules already announced observation windows. German planetary scientist Simeon Smaus, one of CASIS coordinators, hinted in a tweet days earlier that something interesting was being prepared. On paper, the fit between instrumentation, geometry, and timing was perfect. What arrived was silence that threw everyone off and sparked doubts. No images appeared, no brief statements, no preliminary processing. Not even a terse line like, "Data received, analysis ongoing." Official channels remained silent, and some scientists stopped commenting on the topic even in public replies. For a community used to regular updates, that sudden void felt unnatural. However, before speculating, it's worth explaining how the space data flow really works. Part of the delay is imposed by engineering and operations, not conspiracies. The first factor is physical transmission. When MRO takes a series for HiRISE, the information is stored, onboard, and waits for a window with the Deep Space Network, then downloads via Goldstone in California, Madrid in Spain, or Canberra in Australia, at speeds between 0.5 and 6 megabits per second, depending on distance and antennas. A raw HiRISE file can weigh several gigabytes, implying hours of download and competition. For resources with dozens of missions from Voyager 1 to Perseverance and OSIRIS-REx, a delay of a few days is normal and surprises no one. The problem is weeks passed, then months, and by late January 2025, there was no public sign. The second factor is calibration and processing, which aren't just pressing a button. The raw files are mosaics of thousands of frames with geometric distortions, radiometric artifacts, and cosmic ray traces on the detector. Corrections for flat field, hot pixel cleaning, radiometric calibration, geometric stitching, and alignment to the celestial coordinate system are needed. Engineers and scientists handle these tasks, for whom this is just one more item on a list, subject to budget cycles and parallel projects. For routine surface images, this can take weeks. For atypical targets like an interstellar comet, sometimes months. That argument holds until we remember that in extraordinary events, there's usually at least a preliminary report. The public communication protocol is generally predictable. Data received, analysis ongoing. Stay tuned. That keeps interest and transparency in funding use. This time, there was none of that, and the absence is striking. Simeon Smaus, so talkative beforehand, went silent after October 2nd and left direct questions unanswered. Official accounts of Mars Express, Trace Gas Orbiter, and MRO also stayed quiet, publishing no brief mentions. That's where the blackout feeling comes from, though possible causes are several and perfectly mundane. One explanation is a technical failure that messed up pointing or exposure. Maybe the instruments looked in the wrong place, the integration was too short, or the object was much fainter than expected and lost in the noise. Another is scientific caution. If images come out weird, teams might triple check before releasing to avoid a calibration error and damaging their reputation. Third is bureaucracy. Huge agencies, chains of approval, data sharing agreements, and internal committees capable of delaying a release without drama. Fourth is coordinating a big joint premiere, a synchronized package of HiRISE, CASIS, HRSC, and ground-based spectra in a unified publication at the level of Nature or Science. All these scenarios take months and don't contradict common sense. Still, something irritates the observing community, and here we're talking concrete facts. If 3I, Atlas, were an interesting but normal comet, the raw files would already be resting in open archives. The the Planetary Data System or ESA repositories, even before full processing by the teams. The rule is clear. Publicly funded missions must release data to the public with acceptable delays, not indefinite ones. So if the datasets exist, where are they? And why is there no formal confirmation? And if they don't exist due to failures, why hasn't anyone said so explicitly? It's the absence of even a minimal report that fuels suspicion where there could be facts. The most frustrating part is we know quite well what could have been observed. High-rise could distinguish the nucleus structure and, if fragmentation occurred, see separate pieces in the coma. Gas jets would introduce measurable asymmetries, and CASIS with several filters would reveal albedo differences or unusual surface colors. HRSC would capture the extended tail in a wide field, reinforcing system geometry. These aren't idle dreams, but tasks those instruments were designed for. Every day lost reduces the chance to repeat. The ideal observation geometry is gone. The object has already moved behind the Sun and is approaching perihelion, so future geometry will change with Mars's position. What could have been done from that specific angle on those dates is irretrievably behind us, and that's a fact. We have to continue with what's currently on the table: amateur series, ground spectra, and scattered signals from various teams. Fortunately, another source appeared that suddenly raised the debate, while the teams from Mars Express, TGO, and MRO remained silent. Avilov publicly shares his conclusions, and his stance has taken this anomaly story from interesting to a major scientific controversy. Chapter 3: The WOW Signal Bomb. The 15th of August, 1977. The Big Ear Radio Telescope in Ohio scanned the sky at a frequency of 1,420 megahertz within the so-called water hole, the quietest band of the spectrum with minimal noise. It's the ideal range for interstellar communication if someone really wants to be heard. At 11:16 p.m., the detector recorded an unusual burst that stood out statistically. The signal was narrowband, very intense, and lasted exactly 72 seconds, the time Big Ear. The signal was a very intense narrowband and lasted exactly 72 seconds, just the time Big Ear holds the same area in its field before Earth's rotation shifts it. The approximate direction pointed towards Sagittarius, near the border with Capricorn, where the sky background is especially clear. That was enough for a headline, but the details elevated the story. The next morning, astronomer Jerry Eman reviewed the printout and found the sequence 6EQUJ5, an intensity code indicating how many times the signal exceeds the noise. The letter U here means an increase of about 30 times, making it the most powerful event ever captured by Big Ear. Iman took a red marker, circled the sequence, and wrote a single word in the margin: "Wow." That was it. The signal never repeated. The telescope returned to that area days later and found nothing. Other facilities searched for decades with the same result. The source went silent as if it never existed. 47 years later, Avi Loeb, Harvard professor, former head of the astronomy department, and founder of the Galileo Project, published a preprint. The title says it all: Geometric Alignment Between Oumuamua and the WOW Source Region. The key idea is simple and sharp. By extrapolating backward the trajectory of the interstellar object, Oumuamua, it passes very close to the area from which Big Ear detected the burst. This isn't a projection trick, but a specific angular proximity in the celestial sphere. Loeb himself emphasizes this is not proof of origin, but a geometric coincidence worthy of verification. That very coincidence sparked the debate. To put it in perspective, it helps to fix the numbers in words. The WOW coordinates were estimated near 19 hours and 25 minutes of right ascension and negative 27 degrees declination. Considering the width of Big Ear's beam and drift due to rotation, This defines a window in the sky about 10 arc-minutes wide where one could search. Meanwhile, Oumuamua enters the solar system from around 18 hours and 54 minutes, right ascension and negative 31 degrees declination. If we take the velocity vector and extend it backward without gravitational maneuvers, the trajectory crosses an area overlapping the WOW region. The calculated angular distance is about 0.5 degrees, 30 arc-minutes, and over the full sphere of 41,253 square degrees, that implies a probability around 0.6%, roughly 1 in 367. Coincidences happen, but this one isn't trivial. Also, the narrow band at 1,420 MHz challenges natural explanations. Typical astrophysical sources like pulsars and quasars emit broadband signals, not nearly monochromatic ones. If it's not a stellar process, the technological hypothesis emerges. Loeb considers an interstellar probe, a compact vehicle the size of a bus, with a radioisotope reactor or generator producing hundreds of kilowatts and a parabolic antenna between 33 and 66 feet. Such a transmitter could focus the beam with the right geometry. 72 seconds of emission from 1 or 2 light years away would produce that level at the receiver. From there, the kinematics follow. If it were a probe, it would travel fast, several percent of the speed of light, and its continued path could have brought it into the inner solar system in the 2020 seconds. Still, Loeb is cautious. It's a hypothesis, not proof, and the paper's language is deliberately sober. It only states that the geometry is intriguing and deserves independent checks. Verification is direct. If Oumuamua is related to the WOW signal, whether the same object or part of the same mission, it could emit occasionally, not continuously, but episodically, maybe during maneuvers or when passing near specific targets, when the chance of listening is higher. For that purpose, the Galileo Project coordinates a campaign with several radio telescopes. The list includes the Allen Telescope Array in California, partially Green Bank in West Virginia, and if possible, Meerkat in South Africa. The priority is 1,420 MHz, but harmonics like 2,844,260 MHz are also tested, along with other iconic frequencies that the SETI community considers plausible for communication. So far, the result is null, which also informs because it narrows the parameter space. Absence of signal doesn't mean absence of probe. Maybe the transmitter is silent, points elsewhere, or doesn't even use radio. Laser links, invisible or infrared, are also possible. There's another layer adding spice to this picture. In recent years, several teams reanalyzed radio archives in the same region, tracking short, weak bursts, and sometimes hinted at some periodicity. No finding matches the strength of the original WOW, but the set of clues keeps interest alive. If there really were a periodic source and Oumuamua crossed a nearby trajectory, the closest approach to Earth would be a logical window to transmit. October 2024 was that window, and we listened across all reasonable bands. If there was something, we looked late, badly, on the wrong frequency, or simply, there was nothing to hear. Maybe the trajectory coincidence is just that, a coincidence, and what we see is nothing more than a comet with unusual geometry. Still, the question remains, why does this comet puzzle us on other fronts? Alongside radio tracking, spectroscopists report atypical molecular ratios and metallic emissions, inconsistent with cometary norms. Some lines seem more technological than natural, and they deserve examination without sensationalism. The next protagonist is nickel, which appears where it wasn't expected in such proportions. It's not a verdict, but a new layer of data to unravel calmly. It's time to talk about nickel. Chapter 4: Industrial Alloys in Space. Let's talk chemistry precisely and plainly. When astronomers point spectrographs at a comet, they expect a fairly predictable molecular inventory. Water H2O as the dominant nucleus component, carbon dioxide, CO2, carbon monoxide CO, some cyanogen CN, sometimes responsible for a bluish tint, and traces of sodium, calcium, and magnesium vaporized from dust. Heavy metals do appear, but in specific, stable proportions. Iron and nickel usually go together, like in metallic meteorites, fragments of asteroid cores, where the typical mix is about 90% iron and 10% nickel, sometimes 85/15. What you don't see naturally is nickel alone, just like you wouldn't find salt without sodium. So what did Oumuamua's spectra reveal? Clear nickel lines around 341 nanometers, unequivocal and consistent across teams. Iron, however, was absent or below detection threshold. Despite Faye the first transitions being strong, the first data from the Magdalena Ridge Observatory in New Mexico, published early October by lead technician Dustin Trail on spectroscopy forums, yes, that community exists and is competent, were confirmed by independent analysts. Ni the first at 341.5 nanometers with intensity around 3 to 4%, above the continuum. Not a spectacular flash, but real and repeatable. And the oddity doesn't end there. Nickel emission varies markedly with distance from the Sun. Beyond 1.5 astronomical units, about 225 million kilometers, it almost disappears. Around 1.2 astronomical units, it starts to rise. Near 1 AU, where Oumuamua was in early October, it becomes noticeable, and models predict a further increase toward perihelion in November at about 0.65 AU. What mechanism could sustain this behavior? First hypothesis: nickel carbonyl NiCO4 is a real molecule formed when metallic nickel reacts with carbon monoxide at relatively low temperatures, around 50–60 degrees Celsius. It's volatile and photodissociates under ultraviolet, releasing nickel atoms that fluoresce near 341 nanometers. The problem is, it requires nearly pure nickel, available, and a very narrow thermal regime. Second hypothesis: nanoparticles. If the expelled dust contains nickel grains, a few nanometers in size, their thermal physics changes, and solar absorption could favor selective desorption of nickel from mixed iron-nickel grains. In principle, this would leave iron-enriched cores, while nickel forms a detectable gaseous coma. However, photodesorption calculations don't show a strong preference for nickel over iron. Bond energies are comparable, and if one desorbs, the other should follow, unless the initial grain structure is systematically different. Here arises the scenario that makes everyone uncomfortable, because no one wants to say it out loud, yet everyone thinks it. What if the nickel isn't natural? Many human technologies use nickel without iron. Corrosion-resistant coatings on ships, high-temperature alloys for engines, industrial catalysts, ablative materials for heat shields. If you designed a probe for decades or centuries of interstellar travel, facing dust impacts and radiation, you'd prioritize nickel, not pure iron, too reactive. Not a heavy stainless steel, maybe nickel-chrome alloys, or nearly pure nickel layers deposited by design. If that probe slowed by friction in the outer heliosphere, deployed sails, or a propulsion system, it could ablate its skin and release metal atoms into space, exactly the pattern we observe. This isn't a claim, just one possibility among several, and science demands weighing them all before discarding any. The problem is, natural scenarios start to stretch. Each explanation requires special conditions, fine thermal coincidences, or unlikely formation histories. And when you stack anomalies, nickel without iron, possible geometric alignment with the wow, multiple traces, green flashes, the joint probability of all being coincidence shrinks. It doesn't hit zero, but drops. Also, timing matters. The nickel lines correlate with photometric activity. When Oumuamua shows outbursts, hours or days with a brighter coma, nickel intensifies. When activity falls, nickel fades. Normal comets do this with water or CO2. Nickel, however, isn't volatile and shouldn't behave like a switch, unless the source is discrete and localized, like specific jets expelling processed material from particular regions. Or again, the uncomfortable idea, something more like controlled maneuvers than chaotic outgassing. At Lowell Observatory, they tried fitting nickel light curves with standard comet jet models, nucleus rotation, and solar heating. The fit is poor. Outbursts are too sudden and synchronous, as if something switched on, not just warmed up. Most stop here because without more data, high-resolution spectra at perihelion, and detailed polarimetry, you can't prove anything without risking your career. Loeb, however, rates it currently a 4 out of 10 on the INTRA scale. Nickel emission +1. Absence of iron +1. Meanwhile, another oddity adds to the list. It turns out nickel isn't the only strange thing. The CO2 to H2O ratio is completely reversed, way out of norm. This demands a close chemical review of the coma, and maybe re-evaluating assumptions about the material's origin. The chain of hypotheses doesn't justify sensational conclusions, but calls for caution and new observations. For now, the prudent stance is to keep the possibility open, and against that backdrop, the next chapter has a clear protagonist. Nickel was the first clue, but the CO2 to water ratio is the piece that could flip the whole board. Chapter 5. The Anti-Tail Anomaly. Before diving into the chemical nightmare, there's another point to put on the table. On October 8, an unexpected feature appeared in JPL images that changed the tone of the discussion. It's a structure that at first glance looks like a tail pointing in the opposite direction than usual. The physical basis of comet tails is clear. Solar radiation and solar wind push gas and dust away from the nucleus. Charged material forms a very straight ion tail, while dust, due to inertia, describes a subtle curve. In both cases, the orientation is fundamentally anti-solar, without exception under normal conditions. Oumuamua breaks that rule in a striking and documented way. The JPL team, led by planetary astronomer Dennis Bodowitz at Auburn University, pointed the telescope when the object was about 1 astronomical unit from the Sunday. They used the visible light channel of the wide-field camera 3. With a carefully planned 30-minute exposure, the images show a faint but clear anti-solar tail extending about 50,000 kilometers. However, a bright structure also appears toward the sun, technically a forward ray or forward glow. In some enhanced contrast processing, that forward ray outshines the rear tail. The photometric profile of that forward ray is unusual and quantifiable. Measuring how intensity decreases with radial distance, the resulting power law exponent is day, near 4. For normal dust, we'd expect values between 1.5 and 2.5, with a much gentler decline. Such a steep slope implies rapid brightness depletion that doesn't fit simple grain dispersion. The first hypothesis points to extremely fine dust, perhaps submicron or even nanometer scale. At those scales, radiation pressure could redistribute grains before settling into stable trajectories, creating an almost symmetrical envelope that would look like a forward ray from our angle. The problem is the spectral signature doesn't match that simplified reading. Submicroscopic dust scatters preferentially toward blue, a well-known relic effect, but the forward ray's spectrum is chromatically neutral, looking like normal dust, reflecting sunlight, not an ultrafine component with color bias. The second hypothesis appeals to perspective, an apparent anti-tail created by viewing geometry. Back in 1957, Comet Arend-Roland showed a spike seeming to point at the sun, which turned out to be projection through a particle plane. Bodewicz's team examined phase angles, scattering, and orbital position, and yes, there is a configuration that could produce a perspective anti-tail. Still, the observed morphology raises strong objections. Perspective anti-tails tend to be thin, almost needle-like, because we see a thin particle plane backlit. In Oumuamua, the forward ray is wide, diffuse, and extends laterally, as well as radially. Also, Bodewicz repeated the observation 3 days later, and the structure persisted with nearly identical profile and shape. If it were just a geometric effect, changing viewing geometry should alter the appearance. Its temporal stability suggests we're seeing a physical phenomenon around the rend, comet, not a line-of-sight illusion. That conclusion forces us to explore a third explanatory framework. The third hypothesis is gaseous and seems reasonable at first glance. Fluorescent molecules excited by ultraviolet could create an almost isotropic coma, whose apparent asymmetry depends on illumination and column depth. However, spectral analysis shows no strong lines of CN, CO, or OH associated with gas emissions. What dominates is reflected sunlight continuum, that is, dust, not gas. With that door closed, we return to square one. But with fewer degrees of freedom, we have dust that seems to move sunward with a power law profile close to 4 and stable for days. The question stops being what it is and becomes what drives it. If the dust isn't ejected randomly, the logical alternative is a directional source. Cometary jets exist, and missions like Rosetta at 67P Churyumov-Gerasimenko documented dozens of them emerging from active regions. By pure geometry, some jets can point toward the sunlit hemisphere if they're associated with peculiarly illuminated scarps. For 3I, Oumuamua, adjusting the jet direction needed to reproduce the observed ray, including orbital curvature and radiation pressure, the resulting vector, lies about 30 to 40 degrees off the anti-solar axis. That's unusual but possible. The important thing is that this vector, extrapolated back to the nucleus, defines a specific active area on the surface. A sustained active area should leave a detectable thermal signature in the infrared. Spitzer, before its retirement, would have been able to see it, and JWST can do so easily. As far as is publicly known, JWST has not observed 3I, Oumuamua yet, or if it did, the data hasn't been released. That silence echoes the same discomfort found in other parts of this story. Meanwhile, the dynamic argument is what most unsettles modelers. If the leading ray is real dust, directed sunward, that implies a momentum transfer acting as a brake. A jet that reduces orbital velocity isn't just chaotic outgassing, it's a maneuver. No one says this officially, but in emails and private conversations, the question comes up again and again. Could this be propulsion, even if just controlled outgassing, to intentionally direct forces? The honest answer is that we lack high-resolution data and dense time series to confirm or deny it. The perihelion is approaching, and each day activity intensifies. If there are anomalous behaviors, November could be decisive to separate physical illusion, natural causes, and possible control. But first, we need to explain why this object seems so massive and why that introduces a separate problem. Chapter 6: 33 billion tons and the statistics. Let's talk mass calmly, because this is where the models start to wobble. When a comet approaches the sun, radiation heats the icy nucleus and the ice sublimates, going from solid to gas, dragging dust along. That gas escape is violent, chaotic, and above all, generates a measurable force. The pressure of the escaping gas pushes against the nucleus, and although it's not huge, it slightly alters the orbit. This dynamic signature is called non-gravitational acceleration, or NGA, and it's present in practically all active comets. The theory is simple. Observations usually confirm it, and orbital adjustments included as a standard term. With 3I, Oumuamua, however, that piece doesn't fit. Astrometrists from various observatories have tracked its position since its discovery in April 2024, with hundreds of measurements from dozens of sites. When fitting all those points to an orbit, they look for deviations from purely gravitational motion. The result is baffling. The non-gravitational acceleration is essentially zero, below the instrumental threshold. More specifically, it's less than 5 times 10 to the power of -9 astronomical units per day squared, which is the detection limit. If there is NGA, it's so small today that we can't distinguish it from the noise in the fit. The problem is that 3I, Oumuamua, is outgassing and on a large scale. The production rates, meaning how many molecules of carbon dioxide and water it expels per second, are around 10 to the power of 28 to 10 to the power of 29 per second at peak activity. Translated to mass, that's about 500 to 5,000 kilograms of gas every second, second after second. That flow, by pure Newtonian mechanics, should produce a reaction thrust on the nucleus. If the thrust exists and we don't see it in the orbit, only 2 explanations remain. Either the emission is extraordinarily isotropic and all forces cancel out, or the object is so massive that the thrust can't move the observable needle. Perfect isotropy is practically a chimera. Comets aren't polished spheres. They have rough terrain, cliffs, fractures, and localized active zones, so outgassing is never distributed exactly evenly. The remaining hypothesis is mass. And when you crunch the numbers with the observed gas rate and a reasonable specific impulse, a robust figure emerges. The calculation, solving for NGA to fall below the detection threshold, returns a minimum mass of 33 billion tons in compact notation, 33 gigatons. It's not a random value, but the lower limit that reconciles strong activity with the absence of measurable acceleration. Translating that mass to size requires assuming a density. If we take a typical comet density between 400 and 600 kilograms per cubic meter, roughly half that of ice, due to huge porosity, 33 gigatons equate to a volume on the order of 55 to 80 cubic kilometers. If the nucleus were close to a sphere, that would give a diameter of about 5 to 6 kilometers. If it's ellipsoidal, more potato-shaped, as is often the case, the major axis could be between 8 and 10 kilometers. These are significant dimensions. Not enormous, but in the high range for well-studied comets. The context helps place that scale. Comet Halley measures roughly 15 by 8 kilometers, and 67P Churyumov-Gerasimenko, visited by Rosetta, is about 4 by 3 kilometers. Hale-Bopp, one of the giants visible to the naked eye, had an estimated nucleus up to 60 kilometers in diameter. With those references, 3I, Oumuamua, would fall into the large category, but not unprecedented. The detail that changes the flavor of the data is its origin. It's interstellar. And that's where statistics start to creak, because the available sample of visitors from outside is short but significant. To date, we've confidently detected 3 interstellar objects: Oumuamua in 2017, Borisov in 2019, and 3I, Oumuamua in 2024. Oumuamua seemed small, maybe 100 to 200 meters long, and its nature is still debated. Borisov fit the archetype: a comet with a nucleus about 500 meters in diameter, active, and without extreme oddities beyond its origin. Now 3I Oumuamua points to a size of 5 to 10 kilometers, making it 10 to 20 times larger than Borisov and maybe 50 times larger than Oumuamua. With only 3 cases, the third being by far the largest, is at least striking. The reason is the classic power law of populations in asteroids, comets, or Kuiper belt objects. The number of bodies larger than a certain diameter, d, scales roughly, as n is greater than d, proportional to d to the negative q, with q close to 3 or 4. In plain words, small ones are abundant, medium ones scarce, and large ones very rare. That implies that for every 10-kilometer object, there should be thousands of 1-kilometer ones, and millions of 100-meter ones. If interstellar objects follow the same law, and there's no clear reason they wouldn't, we should see hundreds of Oumuamuas before encountering one 3i Oumuamua. Having seen only 3, and the third being the big one, is like flipping a coin twice and getting a mythical eagle on the third try. There are reasonable explanations that soften the surprise, but none erase it. The first is observational bias. Big ones shine more, are seen earlier, and drag our search algorithms. Maybe dozens of small ones escape us simply due to lack of sensitivity. Still, survey performance studies like those from the Vera Rubin Observatory indicate that under favorable conditions, bodies of 200 to 300 meters passing within 1.5 astronomical units should be detected. The second is sampling. With 3 objects, you can't define a distribution, and maybe bad statistical luck is playing a trick on us. We need 20, 50, or 100 detections to speak rigorously, but the current rarity remains. The third explanation revisits physical assumptions. Maybe the assumed density is wrong, and 3i Oumuamua isn't a fluffy icy nucleus, but something denser and rockier, with a density around 2,000 kilograms per cubic meter, closer to an asteroid. 33 gigatons would translate to a diameter of just 3 to 4 kilometers. It'd still be large, but less anomalous. The catch is that a rocky body shouldn't outgas like 3i Oumuamua does. Asteroids lack enough volatiles to close the circle. You'd have to invoke mixed internal structures, a dense core with an icy crust, layered shells, or non-standard processes, which brings us back to special assumptions. Then there's the scenario no one claims, but many examine for internal consistency. If 3i Oumuamua were a spacecraft hypothesis, not conclusion, that minimum mass wouldn't be crazy. Spacecraft are dense by definition, with metal, systems, propellants, and payload. Also, deliberately balanced ventilation, whether coolant, propellant, or waste material, would cancel net accelerations, keeping NGA below the threshold, exactly as observed. It's not proof, just logical compatibility with a pattern. The knot of frustration is that every anomaly admits a possible natural explanation, but stacking them the nickel without iron, alignment with the the leading ray, now the mass natural versions require more and more particular conditions. The inevitable question is how many coincidences fit before parsimony demands another kind of hypothesis. Still, it's wise not to jump to conclusions. We lack detections, dedicated campaigns, and solid comparables. Meanwhile, there's one more piece that tightens the rope and doesn't belong to dynamics, but to chemistry. The ratio of carbon dioxide to water in the coma seems inverted, compared to the cometary norm. If confirmed, the story gets more complicated. So let's talk about carbon dioxide and why that ratio could turn the tables. Chapter 7. The Chemical Nightmare. Here's what we know about normal comets, and it's worth stating clearly. They're born in the outer solar system, beyond the snow line, where the cold immobilizes water and traps a mix of ices. The standard recipe places water H2O as the dominant component, about 80 to 90% of volatiles, followed by carbon monoxide CO, some methane CH4, and carbon dioxide CO2, which usually ranges between 5 and 15% of the mix. That chemical signature betrays an origin in our protoplanetary disk about 4.6 billion years ago. When an object deviates from that pattern, the scientific alarm bells ring immediately. 3i Oumuamua deviates without hesitation. The first spectra from September at Apache Point in New Mexico, later confirmed by Gemini South in Chile, showed unusually strong CO2 lines and weak H2O emissions. Quantifying the ratio gave something like 8 to 1, 8 parts carbon dioxide for every part water. This completely reverses the norm. Not a single solar system comet exhibits such a ratio. The most extreme known case, 103P divided by Hartley 2, barely reaches a near 1-to-1 ratio and is already considered anomalous. 8 to 1 isn't just a rarity, it's a different chemistry. What could sustain such an inversion? First hypothesis, prolonged thermal processing. If 3I, Oumuamua, passed near a hot star or resided for millions of years in the habitable zone of its parent star, chronic heating could have preferentially sublimated water, which is more volatile than CO2 at moderate temperatures. The immediate snag is that in this scenario, CO and methane should also have been largely lost, and both appear in the spectra, modest but present. That is, the heating wasn't intense enough to wipe out everything except CO2. But somehow, it did preferentially expel water. That combination doesn't fit simple models. Second hypothesis, cosmic radiation as a universal chemist. During millions of years of interstellar travel, protons and high-energy nuclei break molecules and trigger recombinations capable of producing CO2 from CO and H2O. In labs and simulations, that excess is obtained under certain conditions, making it plausible. The cost is in timescales and fluxes. To reach 8 to 1, enormous exposure times tens or hundreds of millions of years, or cosmic ray densities far above typical interstellar medium would be needed. That would require close passes to supernovae or star-forming regions. Another special condition added, the more exceptions you stack, the more fragile the explanation becomes. Third hypothesis, different family tree. Maybe 3I, Oumuamua, formed in a protoplanetary disk with different temperatures, composition and metallicity, for example, higher carbon and lower oxygen, which would push chemistry towards CO2. That answer works, but amounts to admitting we don't know the details without visiting its birthplace. While digesting that uncertainty, another clue appears: polarimetry. In late October, the Nordic Optical Telescope in the Canary Islands measured linear polarization in visible light and found a negative value around -1.5%. Negative means the scattered light aligns opposite to what's expected for common dust, and the magnitude triples what's seen in regular comets. That sign and strength are very rare and hard to reproduce with standard mixtures. Negative polarization is usually associated with extremely small particles, smaller than the wavelength, below 100 nanometers, exotic geometries like needles or flakes, or refractive indices outside the usual range for silicates and carbonaceous dust, the NOT team. Tested size distributions, shapes and compositions, and no typical cometary combination reached that -1.5%. They got close with exotic recipes: metallic nanoparticles mixed with CO2 ice, graphene, amorphous carbon, with cavities all plausible on paper. But without prior direct evidence in comets, except apparently and provocatively in this one, the chemistry adds another twist with cyanogen. CN is present. Nothing unusual, but its variation doesn't follow water as you'd expect. If it came from HCN mixed in the ice in 3I Atlas, there are intervals with rising water and flat CN, and others with increasing CN without clear changes in H2O. It's as if CN is coming from a different reservoir, another region of the nucleus, or a different process. Added to this are weak, still unconfirmed hints of carbon chains like C3 and even C4 molecules, which usually require high temperatures, or environments exceptionally rich in carbon. They shouldn't be there, yet they show up. The spectral portrait is starting to look less like a comet and more like something processed. Here, the uncomfortable possibility reappears, without sensationalism. In space engineering, materials are chosen by function: metals for structure, ceramics for insulation, carbon composites for strength, and sometimes ice as radiation shielding. CO2 ice, dry ice, is stable and dense. When it sublimates under the sun, it doesn't introduce complex molecules that interfere with sensors. If a long-traveling object mixed natural materials and manufactured components, part of these signatures would be compatible. It's not proof, but it's not a contradiction either. Meanwhile, the object keeps getting closer, and activity grows every day. Perihelion is where hidden behaviors usually reveal themselves, and there's one last piece that might connect the dots with the Martian mystery. Maybe what was observed near Mars wasn't a single body but several, each with its own chemistry and activity. If that's the case, the current distribution of those satellite objects becomes the key question. Where would they be now? What traces would they leave? And how would their combined effect impact the spectral and polarimetric landscape? This line of inquiry explains why some measurements seem to contradict each other. To know if the lead is real, we'll have to track them down, and that will be the bridge to the next chapter, Chapter 8, The Theory of Precursor Waves. Let's go back to those October 2nd images and what lit the fuse. Stephen Burns's time-lapse and the multiple trails. Yes, and that's a big yes. There really was more than one object in those frames. The first question is, where are they now? And the second, why would they separate? Let's start with the geometry of the encounter with Mars, because that's where the clue is. On the 3rd of October 2024, 3I, Atlases passed at a minimum distance of about 1.7 million miles from the red planet, roughly 7 times the Earth-Moon distance. For an interstellar traveler crossing the system at tens of kilometers per second, that's close to what you'd call a close flyby. That minimum distance, called the MOID, minimum orbital intersection distance, coincided almost exactly in real time. Pure coincidence? Possible, but there's an operational detail that makes you wonder. If you were designing a robotic or other mission to Mars, wouldn't you take advantage of such a close approach to do things? Deploy probes, release payloads, separate modules. Mars's gravity at that moment is a tool. It facilitates course changes, slows you down slightly, and can redirect trajectories, just like the gravity assists we use with Voyager and other spacecraft. If 3I, Atlases, were hypothetically more than a comet, that close pass would be the logical moment for a planned breakup. Small modules could be captured, diverted, or sent on new paths while the main body continues toward the Sunday. Now, the range of scenarios starts with the natural. Comets frequently fragment when solar heating and internal stresses open cracks, or when a planet's tides stretch the nucleus like Shoemaker-Levy 9, which broke apart after grazing Jupiter in the early 92nds, and a few years later, 21 pieces hit the gas giant in a row. At 1.7 million miles, Mars's tidal forces aren't huge, but a fatigued nucleus with cavities, fissures, or rotational stress could give way. If the break happened on October 2nd, the fragments would take nearly identical, but slightly separated paths that, from Perseverance's perspective, would produce multiple trails. It's a clean explanation, compatible with what we know. The problem comes with tracking. If the object fragmented that day, those pieces should be traceable afterward. Sister orbits weakly dispersed, accompanying the main body on its way to perihelion. Astronomers actively search for such signatures, especially in a case this high profile, and so far, no one has confirmed persistent companions. It could be that the fragments were too small and faint, below the limits of current surveys, or it could mean something else. Enter the second scenario: controlled separation. If 3I, Atlases released small units that performed maneuvers, today they could be on completely different paths, not following the parent. That opens up possibilities nothing exotic from orbital mechanics: capture around Mars, insertion into stable intersolar orbits, or even trajectories crossing near-Earth space. For bus-sized or even car-sized objects without visible comas, discovery is tough unless you know exactly where to look. Space is vast, and discrete targets are elusive. Why do some take this framework seriously? Because of HiRISE itself. HiRISE was expected to photograph 3I atlases on October 3rd. The instrument's resolution is impressive, about 12 inches per pixel on the surface, and looking closely, it can distinguish kilometer-scale structures. But its field of view is narrow, around 1.2 degrees, perfect for the main target, but insufficient for escorts separated by tens of thousands of kilometers. If companions existed at 6,000 or 30,000 miles, even a small angular offset would put them out of frame, especially if the separation happened on October 2nd. By the time HiRISE pointed its cameras, the vectors could have diverged too much. Uncomfortable conclusion. Even with flawless images of the main body, if companions exist and haven't been published yet, they could have slipped out of frame. This leads to the million-dollar question. Would 3I atlases have executed a maneuver after perihelion if it's controlled? Perihelion is the optimal moment to radically change orbit. You're closer to the sun, moving faster, and any thrust yields more delta V thanks to the Oberth effect. That's why spacecraft fire engines near perihelion, not whenever it's convenient. If 3I atlases is going to do something, that's the moment, and perihelion falls at the end of November. Right now, during solar glare, the object is unobservable, but when it emerges in late November or early December, we'll have another window. If its trajectory changed, it'll show. Astrometers measure every deviation and every non-gravitational acceleration, no matter how small. This is where the Galileo project by Havilob comes in, specifically preparing for that after. They've set up a monitoring network with telescopes across continents to resume tracking as soon as 3I atlases exit solar glare. They're looking for 3 clear operational signals. First, photometric changes beyond what solar geometry predicts. Dimming or sudden brightening that would reveal internal processes or maneuvers. Second, orbital deviations from predicted ephemerides, a sign of thrusts or unmodeled forces. Third, detectable separations, with smaller objects diverging from the main nucleus. Any of these signals, especially the last two, would quickly raise the team's interest level. If nothing appears exact trajectory, expected brightness, no oddities, that interest level drops and the case normalizes. December and January look like decisive weeks to clear up mysteries. Meanwhile, there's an elephant in the room. The silence of data isn't just uncomfortable, it's repetitive. Repeated patterns have meaning. Between atypical chemistry, high mass, nickel without iron, and the leading ray, the absence of statements and raw data releases adds a layer of uncertainty that colors all interpretations. Maybe there are administrative or technical explanations, maybe they're coordinating a comprehensive package, but that sustained emission is information too, because it changes how we weigh hypotheses. So we have to talk about what's not being said and what that silence implies for the story ahead. Chapter 9: Behind the Sun, the Risk Window. Let's talk about the LOB scale, because amid anomalies, conjectures, and data gaps, Havilob did something unusual. He proposed a public scoring system called the interstellar interest scale, ranging from 0 to 10. 0 means definitely natural phenomenon, and 10 means convincing signs of technology. At the end of October, before 3I atlases disappeared behind the sun, LOB rated it a 4 out of 10. A value that's not loud but significant. For context, Oumuamua peaked around 6 out of 10 for its anomalous acceleration and morphology, then dropped to 3 or 4 as natural explanations emerged. In contrast, Toses and Borisov never scored above 1 out of 10. They were clear, beautiful interstellar comets, but ordinary in behavior. What makes up that provisional 4 out of 10 for 3I Atlas? The geometric alignment with the WOW region adds 1 point, nickel without iron adds another. The inversion of the CO2 to H2O ratio adds half, The leading ray contributes another half. The high mass without non-gravitational acceleration adds one more, and possible multiple trails on Mars. Add half a point conditional. Altogether, it rounds to about 4.5, which LOB prudently left at 4. The crucial thing is this score is fluid and can shift quickly depending on what we observe after perigee. If maneuvers or orbital changes not attributable to modelable outgassing or residual accelerations appear, the scale could jump to 6 or 7. If, on the other hand, the dynamics follow ephemerides exactly and the object behaves like a standard comet, the score will drop to 3 or even 2. The operational problem is that right now, we can't observe 3I. Atlas is in solar conjunction on the far side of the Sun from Earth, and the glare makes it unobservable without risking detectors. This invisibility window started mid-October and lasts until late November, maybe early December, depending on geometry and residual brightness. During that interval, perihelion occurs at about 0.65 astronomical units, slightly inside Venus's orbit, exactly where any comet's activity peaks. It's when outgassing should become explosive, and if anything's gonna change, it'll probably be then. The metaphor is simple. We saw the object enter a dark room, now we wait to see how or if it comes out. What signals to look for upon reappearance? The Galileo project prepared a checklist that's not based on feelings but on observables. First, photometry. Is 3I atlases significantly brighter or dimmer than expected? That would indicate massive fragmentation, premature fading, or unexpected phase transitions. Second, dynamics. Any deviation from ephemerides that doesn't fit symmetric or asymmetric outgassing models will be a red flag. Astrometers will measure positions with precision down to fractions of an arcsecond. Third, spectra. Sudden changes in composition. New layers exposed or different materials activated by temperature would be a strong clue. Fourth, morphology. Appearance of fragments, multiple nuclei, or comas that change shape non-canonically. Fifth, non-thermal emissions. Flashes, pulses, or periodicities pointing to processes other than passive solar heating. The key for December and January isn't just what we see, but also what we don't see. If 3I, Atlases, emerges and behaves exactly like a conventional comet, we'll have learned something too. The previous anomalies, however shocking, admit natural explanations, even if not fully parameterized yet. In that scenario, the score would drop and interest would deflate reasonably, without drama. But if the oddities persist or intensify, we move from an isolated event to a pattern, and patterns are harder to dismiss as coincidence. That qualitative difference, more than any tweet or statement, will move the debate needle, and that's exactly why coordinated monitoring is as important as interpretation. There's another take on the invisibility window that's less romantic and more strategic. If there's any element of control, hiding behind the sun would be the ideal time to do things unseen. Change course, deploy payloads, execute major corrections. It's not paranoia, it's operational logic, the same that guides our own missions when they schedule critical maneuvers during limited coverage periods, taking advantage of the Oberth effect near perihelion when speed is greatest and the same thrust yields more delta V. It's textbook. If something deliberate is going to happen, that's the moment. If nothing happens, the control hypothesis loses weight and the case returns to cometary norms. Meanwhile, a different anomaly emerges, human, that shapes the narrative as much as any spectrum. Prolonged silence, delays, absence of statements, and raw data releases form a pattern, not an anecdote. It could be due to interagency coordination, technical bottlenecks, or methodological caution, and all are valid explanations, but the pattern itself changes how we weigh hypotheses because it adds structural uncertainty to every partial reading. That's why the next chapter isn't just about the sky, but about how we communicate what we see. We'll have to talk about what's not being said and what that silence implies. Chapter 10. What they're not telling us. Let's return to the uncomfortable direct question. Where's the Mars data? Entire months have passed. October, November, December, and January, and we still have no trace from HiRISE. No cases, no HRSC, not a single orbital image of 3I, atlases from 3 satellites. The silence isn't just about images, it's the whole communication ecosystem. No official status reports, no mission team threads, no preprints discussing preliminary findings. Even unofficial channels forums where the planetary community usually shares early data sound strangely muted. It feels like 3I atlases became a topic no one wants to touch publicly. Why is this happening? The range of possibilities goes from mundane to extraordinary, and it's worth exploring without exaggeration. First option: pure bureaucratic incompetence, unsigned forms, stuck pipelines, key personnel on extended leave, budgets exhausted, shifting priorities on the fly. It happens in huge organizations, with lots of inertia, and space agencies are no exception. It's a boring but plausible explanation, though it leaves a sour taste. Second option: textbook technical problems, faulty pointing, wrong exposure times, object too faint, corrupted telemetry packets, or failed calibrations. Teams would be reprocessing, validating sessions, and waiting for another chance to confirm before publishing. All that is plausible and not very exciting. Third option: deliberate scientific caution. If the data shows something unexpected, not necessarily anomalous, but rare enough, it's responsible to triple-check, coordinate with independent groups, and wait. Peer review makes sense the longer the timeline, but it also makes the community more anxious. Fourth option: high-level international coordination. Maybe NASA and ESA preparing a joint concise publication. With mosaics, spectra, and cross-photometry, they prefer a well-packaged announcement over leaks in bits and pieces. That could take months without difficulty and would explain the lack of early updates. Fifth option: security considerations requiring discrete protocols if at any point the data points to something potentially unnatural. Standard review processes would kick in, not conspiracies with classification filters, risk assessments, and advisor consultations. It's unlikely, but possible, and it would justify silence until the administrative process is complete. What we do know for sure is that there are gaps that shouldn't exist at this stage. We don't know the core size from direct measurement. There are only estimates based on brightness and assumed albedo. We don't have the rotation period. Photometry doesn't show a clear pattern, suggesting either very slow rotation, an unusual shape, or a surprisingly uniform surface. We don't know the surface morphology, whether it's smooth or rough, cratered or cliffed. Questions that orbital images were supposed to answer. There's also no confirmation of active fragmentation beyond those possible multiple traces from October 2nd. And we still don't know exactly what happened at perihelion because the object remains behind the Sunday. These are basic observational questions, not philosophical mysteries, which is why it's frustrating they remain open when they should be answered in the coming weeks. However, the situation will unfold in one of two ways. Scenario A: 3I Oumuamua exits perihelion on the expected trajectory, behaving like a textbook comet. Orbital data shows a normal core, and the story is filed as a footnote. The OEB scale drops to 2, interest cools off, and the case becomes part of the statistics. Scenario B: 3I Oumuamua emerges with additional oddities, trajectory deviations, unexpected fragmented structure, or activity that doesn't fit models, and orbital data is delayed or deepens the mystery. In that case, the scale rises to 6 or higher. Pressure for transparency increases, more telescopes join in, and analyses and questions multiply. This is the frontier where speculation meets facts and hypotheses confront reality. By the end of January 2025, we'll know a lot more than we do today whether 3I Oumuamua is a strange comet from an interstellar nursery or something that challenges our assumptions. Meanwhile, we watch, wait, and keep instruments ready for when it crosses the solar glare. Because when 3I Oumuamua emerges from the sun's brightness, what happens next will be the most important chapter of this story, and we'll have to report it in real time, observing alongside everyone else what emerges from the glare in November. We'll know very soon, and even if the answers aren't definitive, at least they'll be better questions.